Section 2.6 is kind of the culmination of derivatives and some of the applications of derivatives. And the title is called Related Rates. And so what we're going to be doing in this section is we're going to be encountering word problems. And if you'll notice, even on the end of this sheet, you have not only a WebAssign work, but you actually have a written work as well. Okay? So this written work you will actually be turning in to Dr. Marsh on Friday when you come to class. She'll be able to answer some questions over it before you turn it in. So if there's, there's not a ton of problems on this list, are there? How many do I have? There's 3. So she's not going to do all 3 of them. That's not going to work for her. But she might do one of them. So if you have problems as you're encountering them over the next couple of days while I'm here, come see me. After that, you're welcome to send me an email or use the Success Center. But these problems are application-based. Everybody has this sort of thing that they're like, kind of like what Kaylee asked. She was like, but what does it mean, right? What is this used for? How can I, with her question earlier, we all kind of want to know what's the point, but then when we encounter those word problems, we're like, oh man, I'm sorry I asked. A little bit, right? Because word problems are hard, and they're difficult. So I want to talk to you a little bit about what related rates process looks for finding these quantities. There's some guidelines for solving a related rates problem. Sketches are really good. You do not have to be an artist, says one who's not. I don't draw very well. But sketches can be really helpful in determining all the pieces of what you know and what you're looking for. Setting up equations relating all of the relevant quantities. There are some geometric equations that you should just know. Like I shouldn't have to tell you the formula for area of a rectangle, right? But if I ask you something about the volume of a sphere, I'm not going to expect that you just off the cuff remember the volume of a sphere. So with a certain degree of just reasonableness, there's things that you should remember because they come up all the time in math, and there's things that I would think that's pretty random. I don't think they would use it. So if I asked you a question on the test, I'd give you that formula, okay? We'll encounter a few more of those kinds of ideas as we work our way through. After you have set things up with an equation, you're going to differentiate implicitly, right? Implicit differentiation, that's what we just did in the last section. But the implicit differentiation will not be dy dx. It will be with respect to time. Something will be changing with respect to time. So you're going to end up with dy dt's and dx dt's involved. And you'll see how that plays out in a moment. The whole idea when you're working with an application problem is you get some sort of a numerical answer that gives you information. So you're going to substitute in values for known quantities and derivatives and then solve for the remaining rate. All right, so the first example is a really good example of one where you should remember a few basic things. So let me just kind of pause for a moment. I know a couple of you are still writing down the screen. Some things that I think that you should remember at this point. I think that you should remember the Pythagorean theorem. A squared plus b squared equals c squared. You should know how to find areas of triangles and rectangles. That shouldn't be something I need to give you information for. Areas of circles. That kind of stuff. Those are some pretty basic things. You've been working with those since early middle school. They crop up, kind of from time to time, and you forget them and you remember them, and I get that. But at this point, they've kind of cropped up enough that you should remember them. In terms of trig, because trig is going to come into play on our first problem here, you should remember the relationships in a triangle. That the sine is the opposite over the hypotenuse, right? That cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. SOHCAHTOA, right? You should remember and you should know how to use that. I shouldn't have to give you that kind of a formula. Okay? So let's take a look at the first example. It's got a fishing example. A fish is reeled in at a rate of 1 foot per second from a point 10 feet above the water. At what rate is the angle of elevation, I'll clarify that if you don't remember that, theta, between the line and the water changing when there is a total of 25 feet of line from the end of the rod to the water? Okay, so you do not have to know anything really about fishing to do this problem because the language is describing shapes that are very familiar shapes. That's how all the problems are going to be. You can imply or push upon them a geometric shape. It tells you that we are 10 feet above the water, so we're going to draw some water. Okay, we can do that, right? and we are 10 feet above it. So right here is 10 feet, and it's not changing. So you can imagine our guy is standing on a dock, or our guy who's fishing or woman who's fishing, whatever, is standing in a boat. The distance between where they're standing and the water is not changing. That's constant, no matter what's going on in the problem. Okay? Now, as they're fishing, the whole point is that the line is changing, right? The length of line in the water is changing, but the height is not changing. And it's really important as you recognize these pieces in the problem to recognize what's constant and what's changing. So we're going to reel the fish in. So here's our person up in the front or on the top, and they're going to reel in a fish. And I'm going to put the line in the water, and I'm going to make it red to remind you that it's changing, just so that it's not the same black constant that I've got from before. So they're changing this. Now, the reality is that as the line pulls in, what happens is that this triangle changes shape. Are you guys with me? Right? I mean, it doesn't like reel in and all of a sudden there's a fish hovering in the air coming along this line. That doesn't work like that. So this triangle actually changes as we work our way along. So it looks like that, and then as we get the fish closer, it looks like this, and eventually it looks like this, and so forth as the fish moves in. All right? It tells us a couple of other things. It says, at what rate is the angle of elevation between the line, that's the red, and the water, blue, changing? So even without the language or knowing what the language means, this is the angle they're talking about, because they tell you it's between the fishing line and the water. So they're asking you a question about this particular angle. We kind of skipped over the rate at the beginning. It says the fish is being reeled in at a rate of 1 foot per second. So what that's telling you is that the red piece right here is getting shorter, right? And I need some variables because this is the red is actually changing, right? So let me call it X. And then well, that's probably enough for now. So this right here, this dx dt in terms of time is changing, and it's being reeled in. So the line is actually getting shorter. So this is -1 foot per second. Okay, because it's decreasing, it's negative. And then the last thing it tells you is that there is a point in time, sometime, when x is equal to 25 feet. It's not a constant all the time, though, but there will be a point in time when it's equal to 25 feet. So at some point, I'm going to need to know that x is 25 feet. So if you take a look at the pieces of information that you have and that you're working with the angle theta, right? Because it asks you to find how the angle's changing, okay? So how the angle's changing means that you're going to be finding d theta dt, okay? How the angle's changing with respect to time. And I need a relationship between the angle theta, the side that I know that's 10, and the side that's changing right here, the red side, which is eventually going to be 25. So what would the relationship be between the 10 side, or between the black, the height of those, the 10, and the length that's actually red? Which trig function relates those two quantities together? What is it? It is sine, right? Because we said before, sine is opposite over hypotenuse. So the sine of theta is my 10 foot. It's not changing, but I don't want to put over 25 because it's not always 25. It's actually over x. It's changing. It's changing at a rate of 1 foot per second. Okay, so this is the trig relationship that exists between the known quantity that's constant and the known quantity that's changing. So what I need to do is I need to take the derivative of this implicitly. So what is the derivative of sine? Cosine. So the derivative of sine theta is cosine of theta. But then the derivative of theta is 1 d theta dt. Yeah. Okay, so the derivative with respect to time. How is theta changing? D theta dt. So anytime I take derivatives with implicit differentiation, all the variables are going to have this, d whatever dt, d whatever dt. Now on the right-hand side, it will be easier to work with this if I write it like that, 10x to the -1. It'll just be easier. Then I can use simple derivative rules. This will be -10x to the -2, but then I have to multiply it by dx dt, because x is also changing with respect to time, because time's the variable here. Time's the thing that's actually forcing the other components to make change to them. All right, so it's kind of messy looking, but the reality is that at this point, I could actually evaluate all the pieces that are there, except for the fact that I don't know what theta is. So let's pause for a moment and ask ourselves, but can I find theta? We already said that the sine of theta is 10 over x. There it is. But the point at which I want to find information about our problem is when x is 25, right? So when x is 25, like when that actually happens, there is a specific value for theta that is not changing. It is constant at that specific point in time. Like it has a specific value. So I can actually find the sine of theta, and it's equal to 10 over 25 for a specific value of theta. And it's just a reminder of how you do that with your calculator. I think I have space over here. You do. There's a button in your calculator that says sine -1. And that's the button that you would use to get an approximation for the value of theta. In radians, you should always have your calculator in radians for calculus. And we want to keep quite a few decimal places of accuracy so that we don't end up losing anything along the way. 4 decimal places is probably enough for what we're going to do. So we're going to do 0.4115. Give me just one more minute and we can plug the values in to finish it up. So over here I had cosine of theta. So now I have cosine of 0.4115 times d theta dt, which is what we don't know, equals -10. The x value was 25 squared, and dx dt was -1. Everything has a value except for the d theta dt that I don't know. And I'm working with something that has like actual numerical components that have context, right? There's context to what I'm working with. So as I'm working with this, decimals are quite appropriate, and your radicals would be inappropriate on this problem. So working through this, and then eventually I would divide, of course, by the cosine of the 0.4115 to the other side. We can find d theta dt. I trust that your calculators will be able to help you work with that. The value that you end up getting is 0.0175. The nice thing about this notation is that it actually shows you units what they should be, because it looks like a ratio. What are your units on theta? What units are we working with in theta? T is time, but what is theta? Radians. So this is radians per, and then what time measurement are we working in this problem? Seconds, because it said feet per second at the beginning right here. So this is radians per second. So this looks like a fraction, right? Radians on top, seconds on bottom, because theta is in radians times in seconds. So it's radians per second at the end. Okay, and then you're finished. All right, so I will post a video of the last 2 examples so you can see how these continue to work. Every problem on these feels somewhat different because it's applications, and that's what the reality is for applications. These are going to be difficult problems. I'm not going to sugarcoat it, all right? So be prepared to spend a little bit of time thinking through these particular problems.